Hello everyone, I'm Ashika Banu. I'm currently pursuing third year in Electronics and Communication Engineering in Kongo Engineering College, Perendurai. Now I'm gonna discuss about the microwave oven project that I developed during the Embedded Systems internship. Topics learned during internship. The first topic is the basics of C programming. The second topic is the fundamentals of embedded systems. And the third one is the requirements for the project, architecture of PIC16F877A microcontroller, brief explanation about timers, matrix keypad, CLCD and ISR. Introduction to microwave oven and its working, implementation and demonstration of the project. Basics of C programming. In this, I learned about the data types like int, float, char and double, printf and scanf functions. In printf, it is used to print the output, and the scanf function, it is used to take input from the user. The second topic is the usage of conditional statements like if else, switch case, and third one is the usage of loops like for, while and do while. Dived into operators and its types like arithmetic, logical, relative and ternary operators. Sixth topic is the arrays. Seventh topic is the need of pointer concept in arrays and its functionality. Types of pointer, recursion and its types, strings and storage classes, preprocessor and macros. Fundamentals of embedded systems. What are embedded systems? Embedded systems is a combination of hardware and software to do a specific task. Example, washing machine, smartwatches, drones, etc. Types of embedded systems. There are four types of embedded systems, namely standalone, real-time, networked, and mobile. Standalone. Standalone just follows the instructions given by the user blindly. Example, let's take a washing machine. Even though we didn't put any clothes, if we start the washing machine, it automatically starts rotating even though there is no clothes in it. So it does not check any specific condition. It follows the instructions blindly. Whereas real time, it follows the instructions as well as provides the real time data to the user. It checks some timings and all those things. Networked. In network embedded systems, it is purely reliable on wired or wireless networks. Mobile embedded systems. In mobile embedded systems, these embedded systems are in automation, like they are movable to any other environment and switchable to any other environments. Microprocessor versus microcontroller. What is microprocessor? Microprocessor is a central processing unit. What is microprocessor? Microprocessor is a central processing unit on a single chip used for general purpose computing, whereas microcontroller, it is a compact integrated circuit that contains a CPU, memory and peripherals for specific applications. Components of the microprocessor. It contains only the CPU, but it requires external RAM, ROM and input-output devices. In microcontroller, it includes CPU, RAM, ROM, timers and input-output ports within a single chip. Applications of microprocessor. Microprocessors are used in computers, laptops and high-performance systems requiring complex tasks. Microcontrollers are used in embedded systems, automation and devices like washing machines, IoT devices and cars. Performance-wise, microprocessor is high processing power capable of multitasking and running operating systems. Microcontroller is optimized for control-oriented tasks, lower processing power. Power consumption. In microprocessor, high power consumption as additional external components are needed. In microcontroller, it is low power consumption designed for Energy efficient operations. Cost. Microprocessor is more expensive due to the need of external peripherals. Microcontroller is cost effective as everything is integrated on a single chip. Components of a microcontroller. Microcontroller's components are sensors, analog to digital converter, digital to analog converter, actuators, human interfaces, diagnostic port, memory, and FPGA. In memory, there are RAM, ROM, EEPROM, and so on. Sensors. Sensors are of two types, namely analog sensors and digital sensors. If we use digital sensors with a microcontroller, there is no need of analog to digital converter since it does not affect the microcontroller. But if we use analog sensors, we must interface analog to digital converter with the sensor as well as microcontroller to prevent the damage. Requirements for the project. The first one is PicSimLab IDE and MPLabX IDE, PIC16F877A microcontroller, 16x4 CLCD display, matrix keypad and timer 2. Now, architecture of PIC16F877A microcontroller. PIC16F877A is an 8-bit microcontroller. It has 5 input-output ports, namely port A, port B, port C, port D and port E. Port A has 5 analog pins. Port A has 6 analog pins and port E has 3 analog pins, in which the 3 pins are read pin, write pin and chip select pin. Port B, C, D each has 8 pins of digital pins each. Port C is used for serial communication and port D is used for parallel communication. It has oscillator and reset circuits of total of 7. The first one is the power up timer, the second one is the oscillator startup timer, the third one is the power on reset, the fourth one is the watchdog timer, fifth one is the brownout reset, and sixth one is in-circuit debugger, and at last low voltage programming. It also has timing generation at oscillator 1 and oscillator 2. It has 35 instruction sets with 2 addressing modes. It also has instruction register. It has flash program memory. It has a 13-bit program counter in which the address of the next instruction to be executed gets stored. It also has an 8-level stack of 13-bit. It has RAM file registers and MUX, FSR register, status register, MUX, and at last W register. It has inbuilt A to D converter. And the peripherals of the PIC16F877A are timer 0, timer 1, timer 2, 10-bit A to D converter, parallel slave port, voltage reference, comparator, user, synchronous serial port, compare capture PWM1, compare capture PWM2, data EEPROM. While coming to the CLCD display, this is a 16x2 CLCD display, but the pins are all same. It is a 16-pin CLCD display in which the VSS is ground and VCC is power supply, VEE is for contrast control, RS register select bit. If it is 0, the given input is taken as a command. If the register select is 1, the given input is taken as a data. That is, it prints whatever we give input as data. Fifth one is read write pin. If this pin is 0, then the write mode is enabled. Then if the pin is 1, the read mode is enabled. And the sixth pin is the enable pin. It activates the data transmission between the microcontroller and the LCD display. Seventh one is the date. 7th one to 14th one. These 8 pins are used for data transmission. These 8 bits is transmitting the 8-bit data. The 15th pin is the backlight LED positive and the 16th pin is backlight LED negative. Timers. This is the timer 2 block diagram. It contains TMR2 register, TR2 register, in which the comparator compares the values in the two registers and sends it to PostScalar. And after PostScalar, it sets the TMR2 flag as 1, and the timer 2 register value is sent to the prescaler. Now configuring and using the timer 2 for delay generation. The first step is calculate the timer count for the required delay. The second step is set the prescaler bits in T2 con as per the delay calculations. And the third one is load the timer value into the TMR2 register. Fourth one is enable the timer to interrupt by setting TMR2 IE bit. Fifth one is enable the global and peripheral interrupts by setting GIE and PIE bits as 1. And at last, finally start the timer 2 by setting TMR2 on bit. Matrix keypad. Matrix keypad is a 4x4 keypad with 16 keys, 4 rows and 4 columns. What is the need for going to matrix keypad instead of switches? Because in switches there is only a one input, but whereas in matrix keypad there is more than one input. So we are going for matrix keypad. Especially for this project we are using 4x4 keypads with 16 keys. It uses 8 pins with row column scanning. It requires pull-up or pull-down resistors. It is used in ATMs, security and automation. Matrix keypad works with Arduino, PIC and ESP32. ISR. What is ISR? ISR is interrupt service routine. It handles hardware inputs in PIC16F877A. ISR is defined using void interrupt in MPLAB XC8. Global interrupt enable must be set to enable interrupts, and specific interrupt flags must be cleared inside ISR. It supports external timer, UART, ADC and other interrupts. ISR should be short and efficient to avoid delays in program execution. Introduction to microwave. What is microwave? A microwave oven is a kitchen appliance that uses microwave radiation to cook or heat food quickly. A magnetron generates microwaves which reflect inside the metal cavity and penetrate food. Water molecules absorb the energy, causing dielectric heating through vibration. This ensures fast, even cooking. Features include power settings, timers, and safety interlocks. Common uses include reheating, refrosting, and cooking. Now, what are the modes of operation in microwave oven that we use here? There are 4 modes of operation, namely micro mode, grill mode, convection mode, and start mode. In micro mode, in this mode of operation, the food is cooked in a traditional way such as defrosting, cooking, reheating. In micro mode, it uses maximum power of 900 watts. In grill mode, it is same as micro mode, but the only difference is it grills the food along with cooking. Convection mode. In this mode, preheating of the oven takes place. Then, after setting the time, the fan starts rotating to indicate the microwave oven is running properly. After the food gets ready, the fan turns off and the buzzer is rang. And the fourth mode is the start mode. It is the default mode of the microwave oven. Whenever the user clicks the start button, the microwave oven starts cooking and the time gets incremented by 30 seconds whenever the start button gets pressed. Now we can see the implementation and demonstration of the project. So this is the code I written to develop this microwave oven project. Here this is main.c for micro mode, grill mode, convection mode and start mode, and required source files and header files, timers, TMR2 and all these things. Now I'm gonna build this. That is built successful with no errors. Let's proceed with the Pixim lab. Now we are switching on the, if you are loading the hex file of the microwave, this is my hex file that I generated. So this is the powering on screen and the four modes: micro mode, grill mode, convection mode and start mode. To select micro mode, we have to click 1. The power is showing 900 watts. It is the maximum power. Now if we set time like 1, 5, the star is used to clear the input. So I am giving star. 1 should be pressed properly and 5. Now hash. This hash can be used to enter the time. Now if we press hash, the fan starts rotating and the timer up counts, down counts. So if we pause, it pauses and starts, and we can also stop. Okay, to again go into the micro mode, again we have to press 1. Power is 900 watts. If we set timer as 1 and 0, and if we press hash, the timer starts. Now time up, enjoy your meal, and the buzzer is rang. So the first requirement is completed. The second requirement is grill mode. To select grill mode, we have to choose 2. We have to set time, let's say 20 seconds. Let's check if the start and pause button works. 5 for pause and 4 for resume. Now the fan also starts rotating. It indicates the microwave oven is on, and when it starts to 0, it counts to 0, the buzzer will be on. Time up, enjoy your meal, it is same. Third one is convection mode. We have to set the temperature. The temperature must be less than 180 degrees Celsius. So let's say we put 1, 2, 4. So this is the temperature I have set. Now I am entering. Now the oven preheats for default of 60 seconds. Let's wait for it. Now we can set time. Let's say when clear. can reset again. Let's say 50. Now the time is set as 20 seconds and entering. Again, the fan starts rotating. Pause button works fine. Start button also works fine. Stop also works fine. That's all. The third requirement is also met. And the fourth one is the start mode. It is a default mode. And if we press 4 again and again, it should be incremented by 30 seconds. See, 54, 1 minute, 21 seconds. And if we keep on pressing the fourth button, it keeps on incrementing by 30 seconds. And once it stops, the buzzer is on and the fan is off. Time up, meal is ready. Can pause, stop, pause, start. Again, if we press start, it will be added 30 seconds. So if we stop, it will be go to menu screen. Now all the four conditions are met and the requirements are met. So that's all about the project. Thank you Emertxe for providing me this wonderful opportunity to enhance my skills in embedded systems. Thank you all.